In this video lecture, we're going to look at hemostasis, or the control of bleeding. This is a three-step process that involves cell signaling molecules in each of those steps. That last step of the process is called coagulation, and that involves an intrinsic, extrinsic, and common pathway. And so we'll look at the interactions of these pathways and how these cell signaling molecules are involved in each of the steps. So first, let's get an overview of hemostasis. It's actually a three-step process again. The first step of that is what's called vascular spasm. This is where the smooth muscle in the damaged area of the blood vessel constricts and then limits blood flow to that area. The next step is platelet plug formations, where the platelets start to stick to each other and to the damaged cell vessel wall, and therefore forming a plug, or think of it like sticking your finger in a dam to stop the water, in this case stop bleeding. The last step is the blood clotting or coagulation. Here we're taking fibrinogen, which is found in the plasma, and converting it to fibrin. Fibrin is like this mesh network of fibers, of proteins that end up forming the blood clot. All three of these steps need platelets involved with it in order for it to successfully form a blood clot. So again, let's look at it in general. Here, let's say we start with a vascular injury. The first step of it, again, is vasoconstriction, that vascular spasm, getting those smooth muscle cells to constrict in the vessel wall where it's damaged. That then the underlying subendothelial collagen that's exposed because of the injury. So think of the subendothelial. Endothelial cells, if you remember, are the cells that line the blood vessel. So these are the collagen fibers found underneath them. The exposure of those make the platelets stick to those collagen fibers, as well as stick together or aggregate, and then they become activated. This whole platelet plug formation sometimes is referred to as primary hemostasis. It happens second. It can also trigger the coagulation cascade, as well as release of tissue factors from the vascular injury itself can also lead to coagulation cascade, or the coagulation process, the blood clot. This is also referred to as secondary hemostasis. All three of these things in combination then result in a nice stable fibrin platelet combination clot that then will plug the hole and prevent blood loss, and then allow for the vessel wall to repair itself. And therefore, once it's repaired, that vessel or the blood clot's not needed anymore. So now we need to break up the blood clot in a process called fibrinolysis. So now we'll look at each stage of this process, starting first with the vascular spasm. Again, this is basically smooth muscle cells constricting, reducing the blood flow to that area. It's going to be triggered by lots of different things. First of all, pain receptors can directly innervate the constrictors, the vasoconstrictors, and cause those smooth muscles to constrict. Injury to the smooth muscle themselves can cause constriction. And then last, the platelets will release chemicals that will cause vasoconstriction as well. So we look at it this way. You can see here, let's say we have a damaged area. The smooth muscle here that's been damaged will reflexively vasoconstrict. The underlying exposed basal lamina will release endothelins. Endothelins will then stimulate smooth muscles to constrict. And then last, the platelets here will end up becoming or sticking to the injured area, or the collagen exposed underneath here. That activates them, which they then release thromboxane A2, which is also a vasoconstrictor. So you've got endothelin from the underlying tissues or the damaged endothelial cells, the platelets releasing thromboxane A2, all of that plus the smooth muscles reflexively vasoconstricting is going to end up resulting in vasoconstriction and thereby decreasing the blood loss because you don't have as much blood flow to the area. The next step along the way is platelet plug formation. This is going to involve multiple steps as well. We've got to get the platelets to adhere or stick to the damaged vessel. Then we've got to get them to stick to one another, called platelet aggregation. This in turn then, once they aggregate, activates these platelets as well, and then they start releasing all kinds of substances. Serotonin and thromboxane A2 are two of these. Both of these are vasoconstrictors, so that they can get the smooth muscle to constrict and reduce blood flow to the area. And they also help in causing platelets to aggregate together. ADP is another one for platelet aggregation and also to stimulate secretion of other substances from the platelets. Platelet-derived growth factor is another substance released by platelets. This is the idea to get the vessel to repair itself. Calcium is released, which we need for platelet aggregation as well as blood clot formation. And then platelets finally will release clotting factors, which we need for clot formation as well. Here we can see what's going on with the platelets. First of all, you can see here we've got tissue that's been damaged because of whatever break in the vessel wall. Over here is where the blood vessel is still in good shape. To prevent any platelets from sticking to areas where it's in good shape, the blood vessel or the endothelial cells will release prostacyclin and nitric oxide, which act as platelet repellents, because we don't want platelets to stick where there's no damage. We just want them to stick here where it's damaged. The broken vessel exposes collagen fibers in the basal lamina, which is that underlying layer of epithelial tissue, and that allows the platelets to start sticking or adhering to that collagen using what's called von Willebrand factors. These just basically link the platelet to the underexposed collagen. That then in turn causes the platelet to start releasing ADP and thromboxane A2. The thromboxane A2, remember, is involved in vasoconstriction. Both of these are involved in getting platelets to become activated, so they start changing their shape. Notice they go from this nice round shape, now they're this kind of weird, bizarre star shape with these extensions out. They start releasing more ADP and more thromboxane A2, and in turn the platelets start to adhere to each other by forming these fibrinogen links. So they have fibrinogen receptors in the red, and then the white here, think of that as the fibrinogen in between them. So imagine these guys as holding hands, but instead of holding hands directly, they're holding onto each other, say with a napkin or a string in between them. So that if your hand is the fibrinogen receptor, the napkin then is the fibrinogen itself. And so they start linking to each other using their little fibrinogen napkins and holding on and linking more and more together until you finally get this platelet plug formed and the whole area is filled with platelets. Again, this is a real positive feedback kind of mechanism, because once you activate some platelets and they start to aggregate, they'll release more stuff, which gets more platelets to become activated and start aggregating, which means more thromboxane, more ADP, which means more platelet aggregation. So it just feeds on itself. The only thing that stops this platelet plug forming indefinitely is the fact that we've got areas over here on the side, which is nice and smooth, secreting anti or platelet repellents. The next phase of this is going to be then the coagulation phase. In the coagulation phase, what's going on is we're going to be finally converting fibrinogen into fibrin. Remember again, fibrinogen is a plasma protein that's floating around in your blood. It's soluble, mind its own business. It in clot formation is going to get converted to fibrin, which is insoluble. And as a fibrin, think of as long threads that mesh together with the platelets and form the blood clot. So we have this long cascading kind of process to get us to that final step of converting fibrinogen into fibrin. Now, the things that are involved in getting blood clot formation is procoagulants or clotting factors. these clotting factors are made mostly by the liver in an inactive form. And so they're just floating around in the plasma, minding their own business. And it's the conversion of these clotting factors from an inactive form to an active form that triggers the whole clotting mechanism. Now, to do that, we need a bunch of stuff. One, we need vitamin K, because vitamin K is necessary for the making of these clotting factors in our liver. We need calcium in order to get the clotting process or cascade going and keep going. It's basically involved almost in every step along the way. And then the whole idea is, again, is a cascade. So it's like one factor will activate another factor, which will activate another factor, which will activate another factor, and so forth and so on. Now, this table over here shows a list of all the clotting factors involved. You can see that the clotting factors are named according to a Roman numeral or by a name. Now, we'll use a mixture of the two. In some cases, I'll refer only to numbers. In other ones, I'll only refer to names, like particularly fibrinogen and prothrombin. The rest, really, I'll be using the Roman numerals for those. Now, unfortunately, the Roman numerals aren't numbered according to the order in which they activate each other. They are numbered according to the way they were discovered. So it makes it very confusing, but we'll work through and I'll show you a shortcut or kind of a way I remember which ones are involved where. So let's first look in general about these pathways that we can get to clotting. There's basically two pathways, well, three if you count the common pathway, but two pathways to start it. We have an extrinsic pathway or system and an intrinsic pathway or system. The extrinsic pathway is triggered from tissue injury. So the tissue itself secretes substances to trigger the extrinsic pathway. So that's why it's extrinsic. Its beginning starts with something outside of the blood. The intrinsic cascade starts within the blood. That is, the platelets themselves and the plasma factors, or the clotting factors themselves, start the intrinsic system, or can start the intrinsic system. So that way it's inside the blood or intrinsic to the blood. Both of these, whether it's extrinsic or intrinsic pathways, end up forming or leading to the activation of factor 10 and prothrombin activator. That gets us to the common pathways. Now the common pathway then is shown in the rest of this slide, which we'll talk about later. But notice that finally the end step here is the formation of fibrin. Now both of these cascades, the intrinsic and extrinsic, are going to work together, but we're going to start with one of them and show how the one feeds into the other. So we're going to start with the extrinsic pathway. Again, this one starts or is initiated by a tissue factor that's secreted by the damaged vessel wall. This tissue factor then in turn activates factor 7. So here's 7 inactivated. Notice now it's activated. 7 in turn activates 9 as well as activating 10. Okay, so once we have 10, this is kind of the end of our extrinsic pathway. Down here, this is going to be our common pathway. So once I get the extrinsic pathway done, or factor 10 activated, factor 10 is going to be involved in getting prothrombin converted to thrombin. Thrombin in turn converts fibrinogen into fibrin. Well, it only makes small amounts of fibrin, and I'll come back to this, why the small amounts, later. But again, to review this then, tissue factor gets 7 to be activated. 7 in turn activates 10. 10 converts prothrombin to thrombin, and thrombin converts fibrinogen into fibrin. Now you'll also notice that 7 activated goes off and to the intrinsic pathway, as well as thrombin will be involved in the intrinsic pathway as well. Okay? And let's look at that one next then. Here's the intrinsic pathway. Now the intrinsic pathway starts when the subendothelial surfaces or the negative charge on the surface of the platelets or a negative charge on the surface of glass, so say inside of a test tube, all of those things will cause factor 12, which is basically floating around in the blood. Remember, it's an intrinsic pathway, so this starts with, notice the inside the blood, it becomes activated. 12 then in turn activates 11. 11 in turn activates 9, and then 9 in turn activates 10. Now, look where the feed-in from the extrinsic pathway comes. Here's thrombin that I mentioned from the extrinsic pathway. He can come in turn and activate 11, or he can activate 8, which will also activate 10. And in turn, he will activate 5, which will activate, or excuse me, will be involved in combining to get prothrombin activated. Now, 7 from the extrinsic pathway in turn will also activate 9, and then 9, remember, activates 10. So we've got a lot of different combinations of things that happen. So again, if we go back, 12 becomes activated because of exposure to the subendothelial cells, negative surface of the platelets, negative surface of the glass, and 12 then in turn activates 11, 11 activates 9, 9 activates 10. And then just keep in mind that thrombin and 7 from the extrinsic pathway will come in and also get this intrinsic pathway going as well. I'm not having you detail, specifically where in the pathway, just that it's involved in it as well. Now, once we get 10 activated, we're back to the common pathway. Prothrombin converted to thrombin, thrombin converts fibrinogen into fibrin, but this time I'm going to get large amounts of fibrin. Okay? Now, the intrinsic pathway is much slower because you've got these multiple steps. You're going from 12 to 11 to 9 to 8 to 10. If I go back up, the extrinsic pathway is much faster because you're only going from 7 to 10. Boom, done. So this one's much faster in getting to the common pathway than the intrinsic one. You got a lot more steps here. However, the intrinsic pathways can produce a lot more fibrin because of this idea of what's called enzyme amplification. Okay, we've seen this before, but the idea when you start out with factor 12, if I have 10 of these and each one activates 10 11s, that's 100, and 10 of these means 1,000 9s, then means 10,000 8s, 100,000 factor 10s, a million prothrombins, 10 million thrombins, 100 million fibrins. So for every step, we just get this cascading amplification going on. So the more steps you have, the bigger the amplification. That's why we see, again, backing up on the slides, if I'm only going from tissue factor to 12 to 10, I only have 2 steps here. I'm not going to get much fibrin made. Extrinsic, I'm going 12, 11, 9, 8, 10. That's a lot more. So I'm going to get a lot more fibrin made from the intrinsic pathway. Now the common pathway we've seen a little bit, but let's look at that too. Factor 10, remember, is activated. That's going to get in combination with 5 and some phospholipids and make what's called a prothrombin activator. The prothrombin activator converts prothrombin to thrombin. So it's really factor 10 plus a couple other things, again, that gets prothrombin, which is one of those plasma proteins just floating around, to become thrombin or activated to thrombin. Thrombin in turn then is in charge of converting fibrinogen to fibrin. Now thrombin will also, remember, feed into the intrinsic pathway and speed it up, as well as it converts factor 13 into an active form of factor 13. What 13 does then, it gets the fibrin to make this cross-linked fibrin network. Imagine instead of just a bunch of long strings of fibrin, that the fibrin has little hands sticking out that can grab other fibrin strings. And so you get this cross-linked kind of structure, which is much stronger than not having that cross-linking involved. Now, the interaction of the two then are going to be highly involved. The idea, again, is you have tissue damage here. That's going to trigger, that tissue factor triggers the extrinsic pathway. The extrinsic pathway, then you're going to get some thrombin formation, which means I get some fibrin and a little bit of a clotting going on. Remember, this is only a two-step process, so I don't get a ton of fibrin made. But that thrombin I make from the extrinsic pathway is going to then trigger the intrinsic pathway, along with other ways to trigger the intrinsic pathway too. But that thrombin will feed into the intrinsic pathway. That thrombin then will stimulate the intrinsic pathway to make more thrombin, which in turn can come back and get the intrinsic pathway to even make more thrombin, which means I can make more thrombin, and it kind of loops back here over and over again. So the more thrombin I make, the more stimulation of the intrinsic pathway, which means the more thrombin I make, which means more stimulation of the intrinsic pathway, which means more thrombin, and you see it accelerates more, plus the multi-step layers of the intrinsic pathway. All that together means I'm going to make a huge amount of fibrin, and I make a lot of fibrin, so I'm going to get really good coagulation going. Now from there, so we need to get a little bit more going on with the clot, and that's what's called clot retraction. Right now, all we've done is we've got some platelets sticking together and forming kind of the platelet plug, and mixed in among that in the green, you can think of that as this fibrin gel or threads running around. But we need to get this more concrete, more solid in nature. So instead of being a gel, we really need to get rid of some of the fluid contained within this clot as it is right now. So the platelets actually have actin and myosin myofilaments inside of them, just like muscle, actin and myosin. And so they contract, and so you can see here, think of this platelet pulling in, and it's going to pull in on the fibrinogen fibers that it's linked to, which is cross-linked with other fibrin. And so when that platelet contracts, it's like squeezing everything together, squeezing out the serum, the fluid portion of the clot, and thereby making it much more strong. And then also, remember, because the platelets are stuck to the wall of the blood vessel and you constrict those, it's going to pull the damaged or ruptured edges of that blood vessel more closely together and help close it up more and become a much more effective clot. So that's what hemostasis is all about. What we're going to turn to next is looking at how we prevent unwanted blood clots and how the blood clot is removed.